Good morning. I'm John Douglas, Business Development Director for Element Digital Engineering. I'm joined by Scott Edmond, who's one of our computational fluid dynamics experts. He's volunteered to answer some questions, sort of frequently asked questions around the subject of COVID ventilation modelling. Good morning, Scott.
Good morning, John.
Thanks for doing this.
Yeah, no worries.
That's quite an exciting service. I think people will have lots of questions, and I think we'll try and answer some of those now. So I don't know. Let's start with could you try by trying to explain the concept of computational fluid dynamics and possibly how it's being used for ventilation modeling?
Yeah. So computational fluid dynamics is quite a broad topic, but at its core, it's basically taking the governing physical equations of fluid dynamics and using computational methods and numerical methods to enable us to solve those for practical problems. The issue that we've got with fluid dynamics is that the equations themselves are quite complex, and to try to solve them without the help of computers is really limiting in terms of what problems you can do with them. But computational power has come such a long way in recent decades that we can now explore many different types of practical problems. And as you said, one of these types of problems is ventilation modeling. So that's quite a hot topic at the moment with the COVID-19 pandemic. And what we can do is we can take different enclosures, so different spaces like offices or public spaces and things like that, and we can apply different boundary conditions that are representative of the types of conditions that you would see in these places. And we can use that to extract different pieces of information that are quite useful for understanding, how effective ventilation systems are at extracting air and therefore extracting the virus, and how much of a risk people within those areas are at being exposed to the virus. So yeah, it's quite useful in this space.
That's really interesting. So basically, you're modeling the flow of air through a space, and whether that's an office or a factory or an airport, and you can see how the virus is basically building up in areas where there might be stagnant air, or where the air ventilation system is extracting it. I guess at that point you can then start to look at how we might solve that problem.
Yeah, exactly.
Right. So what sort of parameters are we modeling then?
Yes, so we model lots of different parameters. The main one really is we're interested in what the flow field and the space is doing. We're also interested in some situations in the temperature field, and the two of those things can sometimes be related. So what we can do is we can model both of those things to get an overall picture of what the air within a room or an enclosed space is doing. And then from that, we can infer different things about how effective the ventilation systems within those rooms are. So we can look at things like the streamlines in the room to understand how effective the ventilation system is at mixing the air. Or we can look at something called the mean age of air within the room to understand how long, on average, air actually stays within the room before it's extracted. And then obviously that's quite important in the context of COVID-19, because the longer the air stays within the room on average before it's pulled out, the more chance there is for somebody with the virus, the more chance there is for them to spread that to other people and other people to actually contract the virus. The quicker you can extract that, the lower that risk is. And that's what this is all about. It's about understanding the risk with a given ventilation strategy.
Interesting. So basically, you're looking at the room and what's in there, and obviously heat sources are going to affect the airflow. Ventilation in and out is going to affect how long the air stays in there.
Yeah.
Open windows, open doors, and that type of stuff. But so that it sounds like it's quite a comprehensive service, but there must be some limitations. I don't know if you can think of any sort of practical limitations of what we can and can't model.
Yeah, I mean, practical limitations really come down to what the computer can solve in a reasonable amount of time. Obviously, the bigger your problem is, and that's both physical size and as you said, like number of heat sources and complexity of the configuration of the room, and indeed how many configurations we want to study. Like all these things are practical limitations. Like we can only study so many different configurations, but that's where this comes in as sort of like a supplement to the overall COVID risk assessment that we offer at Element. So our occupational hygiene specialists will narrow down the range of sort of practical high impact solutions, and then we can look at them in more detail with the ventilation modeling.
Okay, that's really interesting. So that is interesting, because I mean, I guess it's feasible to model all kinds of stuff. Like if you're looking at a railway station and you've got people moving around and doors opening and closing and that type of stuff, and lift shafts going up and down, and all of that is, I guess it is possible to model it, but it's really expensive to actually to solve those scenarios. So
Yeah,
working with that sort of the other teams allows us to pin down exactly what scenarios need to be modelled and where we
yeah, exactly. And it's also a question of where is the value. Like in an office, you're going to get people moving around, but more often than not, for most of the day, people are going to be sat at their desk. So, is it worthwhile trying to model somebody moving about a room when you could do it for a lower cost, probably a higher accuracy as well? If you just consider them stationary, sat at their desk, you're probably going to get more value out of the latter.
Yeah. Okay. So what I mean, if people wanted to try this out for their workspace or their railway station or their airport or whatever the building happens to be, what sort of things will they need to help us to build a model for them?
So I think the most basic requirement for us is obviously to have a computerized model of the space itself. So that's normally a CAD model, like a 3D CAD model or something like that. At a bare minimum, we could get away with sort of like a floor plan, and we can build up the rest. But yeah, that's sort of the base element that we need. On top of that, it really comes down to a case by case basis. What the particular problem is. We're interested in understanding things like occupation, how many people are there, where are they likely to be situated, how crowded is a room for a given size of room. Then we can also look at things like, as you mentioned, heat sources. So, people themselves can sometimes be a heat source depending on the temperature and stuff. That might be important. Then you've got things like high performance computing equipment. They quite often give off a lot of heat. And again, that might be an important factor in the overall flow field of the room. Even things like a south facing window, we might want to include the heat transfer by radiation from the sun and that sort of thing. So yeah, it really comes down to, a case by case basis at that point.
Okay, interesting. So, I mean, obviously we need some information about the building, but generally it comes down to some pretty simple rules around, things that are going to affect the airflow and where it goes in, where it goes out.
Yeah, exactly.
All right. So, what sort of costs are we looking at?
Again, it really depends on the specific case. It scales with the complexity of the model. And what we're looking to include and get out of it. So it's hard to kind of pin down a cost. I think it would have to be, contact us and we'll discuss the requirements in more detail with you.
Yeah, I guess that's all. I guess on that then so a small office with a few things going on in there is going to be a lot cheaper than modelling an airport.
Yeah, exactly. And it's also worth mentioning that we do have different modeling strategies that we can employ. So some of them are lower cost, faster to solve. Some of them are more in depth and detailed, and therefore more expensive and take longer to solve. So there really are so many different factors that we have to look at it on a case by case basis.
Okay, right. And so I guess just to finish off then. So if a customer was interested in doing this and they thought it would help, what exactly would we deliver? What would they get as a result of employing us to do this type of modelling?
So I think what they get out of the COVID-19 modelling is really they get the wider risk assessment that's done by our occupational hygiene team. but then that's supplemented by this additional analytical step where we can look in more detail at the recommendations that they're proposing, and we can get insights that maybe you wouldn't be able to get without the computational fluid dynamics. And what that might look like is, you know, we can plot things like the velocity at an instant in time in the room, and we can identify areas with stagnant air, and you know, as I said, we can calculate the mean age of air in the room, and that's a good indicator of how effective your ventilation system is. And then there's other things as well that you can extract from this type of thing, like how comfortable people would feel in the room in terms of thermal comfort, you know, with the difference in temperature, you know, depending on where they're sat with respect to the different ventilation systems. You know, if you're sat underneath a mechanical ventilation system and you've got cold air blowing down on you, then you know, you might feel uncomfortable, and that kind of thing, you can get an insight into that as well with this type of study. So yeah, there's lots of things that we can do.
Yeah, I guess that's quite important, isn't it? It's easy to focus on clearing the virus or just ventilating the room as much as possible, but actually it comes down to people feeling comfortable as well as safe, right?
Yeah.
Okay, that's really helpful. I hope that answers some of the basic questions that a lot of people might have. Thank you very much.
Yeah, thank you, John.